Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for talented high school students. We all know how to count, right? Or do we? In this video, I want to tell you what is counting mathematically and introduce the notion of bijections, which is what you need to give the mathematical basis for counting. Okay, so let's start with a very simple example here. And here we see 4 apples. And what do we do when we count? We just go 1, 2, 3, 4. But what is that mathematically? Can we have a language to express that properly? Okay, so if we're going to do that, what we'll do is we're going to start with a set 1, 2, 3, 4, the things that we use to count. So let's look at the set 1, 2, 3, 4. And the best way to say this is counting 1, 2, 3, 4 is to have a function from this set of 1, 2, 3, 4, these 4 numbers, to this set of 4 apples. So the function, what does it do? If you input 1, you map it to this apple. If you input 2, it outputs this apple. If you input 3, it outputs that apple. And if you input 4, it gets you that apple. Okay, and that's the process that I have just described. So often in enumeration theory, we have a symbol for this set here. It's going to be denoted just brackets 4. And also, of course, we want to be able to count more things than that. So it's good to introduce the more general notation. If you have some natural number n, we use this to denote 1, 2, 3, all the way up to n. Okay, so the way we're going to describe counting is as functions from something like this, a set like this, to the set that you want to count. And the question is, well, this is done via some sort of function. What functions can you use? Well, we're going to have to introduce some terminology to say which functions you can use. So now we're going to look at 2 sets, A and B, and we're going to look at a function f from A to B. And I'm going to introduce the notion of a pre-image of this function. So what we're going to do is we're going to look at something in the target space of this function. Okay, so in the what's called the codomain here. So it's a little element, so a little b, and we're going to look at the pre-image of that. Okay, so what's that defined to be? That's going to be defined to be all the elements A inside the domain of this function, such that f of A is equal to B. Okay, so it could be empty, it could be the empty set. Whatever it is, it's a set of elements inside the domain. And one way to think of it is that if you fix this b here, you look at this equation f of a equals b, and you're just finding all the solutions to that equation. So that's another way of thinking of what the pre-image is. Okay, so let's have a look at this example here. We have a function from this set, 1, 2, 3, 4, to this set of 4 apples. If we pick something in the codomain, like this apple here, what is its pre-image? Well, the only thing which gets mapped to it is the number 3. So the pre-image is going to be the set just consisting of this number 3 here. Okay, so now what types of functions do we want to look at, we want to count? So the first thing that we want to do is we make sure that when we count, we've counted, in this case here, all the apples. Okay, so we don't want to go 1, 2, 3 and miss out this one here. So what does it mean that we've counted all the apples? So in terms of general functions, if you want to make sure that you count all the apples, the types of functions you're interested in are what are called surjective or onto functions. So what's the definition of a surjective or an onto function? Okay, function f in general between 2 sets A and B is surjective or onto. So, okay, they're 2 words for the same thing. If f inverse of B is not empty for any element B in this codomain. So in this case here, it means that if you have anything in the codomain, any of the apples here, you've counted it at least once. Okay, there's some number that maps to it. Okay, so you've counted it. So that makes sure that you've counted every single one of them. Okay, so that's good. So for the types of counting functions we want something which is a surjective or onto map. But the other thing that you want to make sure is that you don't count an object twice. So you don't want to go 1, 2, 3, 4, 5. Are there 5 apples? Okay. So how do we describe the functions which will not overcount and count something twice? So that's in this notion of what's called an injective or one-to-one function. So what's an injective or one-to-one function? Okay, so that's the case where when we look at this f inverse of b, these preimages, f inverse of b has at most one element for any b in B. Okay, so if you went 1, 2, 3, 4, 5, okay, and you double counted this one here, then 3 gets mapped to this apple and 5 gets mapped to this apple. Okay, so the pre-image of this apple now becomes 3 and 5. That's more than one element. Okay, so to make sure that you only count each element once, you want to make sure that these pre-images, okay, for every, in this case apple, but in general for every little b inside B, has at most one element. Okay, and the final thing, of course, that you want, if you want a counting function, right, is basically a function from something like this to the set that you're counting. You want it to be both surjective and injective. And if it's both surjective and injective, that function is called bijective or one-to-one correspondence. Okay, so a function f is bijective or called a one-to-one correspondence if it's both one-to-one and onto. So I guess the one way to describe what that means is the following. So one way of saying onto is that the pre-images of any element in the codomain is non-empty, so it has at least one element. And injectivity is saying that the pre-images of every element, little b, has at most one element. So if you have both of them, that means the pre-images of every element has exactly one element. Okay, it has a unique element inside each of these. And what were these pre-images? They're just the solutions to this equation. If you fix this b here and you solve f of a equals b, they're the solutions. So that means that you just have a unique solution to f of a equals b for every b. That is, f of a equals b has a unique solution for every b in B. Okay, so now we have the terminology to describe our counting function. Okay, so basically if you have a set, you want to count it, okay, and you want to say there are n elements in there, whatever n is, whether it's 4 or some other natural number, okay, then what you need is you need a bijective function from this set here, like this, to the set that you're counting. And just one thing here, I said that this is the definition for all natural numbers for this set, okay, so just to emphasize, so what is this when n is equal to 0? Well, this here is going to be just the empty set. So for A and B, you're allowed to have empty sets in there as well. Okay, so that's the notion of counting. And now I guess the key question though is, well, I counted using this function here, but I didn't have to count this way. I could have gone 1, 2, 3, 4, or 1, 2, 3, 4. And of course you know that it doesn't matter how you do it, you always end up with the final answer of 4. And then the question becomes, well, we know that's certainly true, but can we prove that it's true? Okay, and now the point is that we've set up the language mathematically in a proper way where we can actually try to find a proof of such a result. We can now define the cardinality of a finite set A, which is just a fancy mathematical word for the number of elements in such a finite set. And it's based on the little proposition definition that I'm going to give you here, and this idea of a counting function, which is a bijective function. Okay, so suppose now we have a set A and we want to count the elements in there, and we have this counting function f from this set n or bracket n to A, so that's a bijection. And we suppose we also have another one, g from m to A, so that means that we're counting the number of objects here, and we would expect this to be n because of this counting function, but it's also m by this counting function, so they better be the same. And the proposition states that yes, we do have m is equal to n. So this is something that you can prove. And then that common value for all these different bijections that you can have from sets like this to A, if you take that common value, m or n or whatever it is, okay, that's denoted with these absolute value signs around A, and it's called the cardinality of A. Now, I'm not going to prove this proposition here. You can find the proof on the activity sheet in the Extension 3 Mathematics website. But that's the definition, and it relies on a proposition that you have to prove to make sure it's well defined. And basically, what it's trying to say is that it doesn't matter what order you count the objects, you're always going to get the same number. And the mathematical way of stating this precisely is through this proposition here. So the following proposition also tells us a little trick about how you can count objects. And it's something that you actually use all the time, but now we can phrase it mathematically precisely. Okay? And it relies on the following more general sort of result. Okay? So suppose now that we have f and g, they're going to be two bijections, so two functions which are both one-to-one and onto. F goes from A to B, and g goes from B to C. In this case, we can take what's called the composite function, and this is denoted g little circle f, or sometimes we drop the little circle. Okay, so both notations are used depending on the context. And this is basically a function of a function that you should have seen in calculus with the change of variable. So this will go from A to B to C, so it will go from A to C. Okay, so you'll input something inside this domain of f, so that's a little a, and you can apply f to that, and that'll get you in B. And this is in the domain of g, so you can now apply g to that, and that gives you g of f of a. So it's a function of a function, and this function of a function is called the composite of those two functions, and it's denoted g little circle f, or just gf sometimes as well. Maybe I'll write that in. It's also denoted gf. Though sometimes this can be confused also with the product of two functions, depending on the context. Okay, so in this case here, it's unlikely to cause confusion, but if you're worried about that, then you use this notation here. And it's just a function from A to C where you do function of a function. Okay, so how does this help us to count? So let's look in the special case where A is going to be one of our counting sets, 1 up to n, okay? So if you have a bijection from this n to this b, okay, this n to this b, then that means that this A has n elements. And then if you have a bijection between B and C, okay, that means that by this proposition here, this first part, you have a bijection from A to C. So they have a bijection from this bracket n to C. So that means that C also has n elements. So that means that if B has n elements, and you have a bijection from B to C, so these two sets B and C are in bijection, then they will have the same cardinality, okay? So if B has n elements, then C also has n elements. Okay, so that's often a useful trick for counting elements in a set. Sometimes you have a bijection between two sets, and in one of them it's easier to count than the other. So I want to present to you an example that we've seen previously in this playlist and is on the Extension 3 Mathematics website, and that occurred when we were counting monomials, and we used it implicitly without invoking this proposition, but really this is the proposition which underlies why it works. So let me just remind you what this is. So what we're going to do is we're going to look at non-negative integer solutions. So firstly, I guess we'll start with a little n, which is a natural number, and we're going to look at solutions to d1 plus d2 plus all the way up to dr equals n. Look at solutions to that where this d1 up to dr are natural numbers. So I'm going to write this as a set. So the way I'll do this is A is going to be the set of all. You want R tuples of these numbers, D1 up to dr. And this is inside, well, it has to be an R tuple of natural numbers. So n to the R, okay? So this is the symbol for the set of all R tuples, D1 up to dr, where each of these is inside n, which is the natural number. So each D1 up to dr is a natural number. And we want to look at the set of all those which satisfies this condition here. So that's our first set. And one of the things that we counted was, we counted what this is for each n, okay, for each n. And the way we did it in the video on counting monomials is we used monomials to do it, because then we can bring into play a natural generating function. So what's that in this case? So we're going to look here at the set of monomials, monic ones, monic monomials, m of x1 up to xr, so they're going to be r variables here, of total degree n. So that is m of x. If you substitute x for all of them, you get x to the n. Okay, and the point is that these two sets, they have the same number of elements, and that's because there's a bijection between them. So let me give you the bijection. So we have bijection, and I'll also in the bijection hopefully remind you what a monic monomial is if you've forgotten. Okay, so we have bijection, and I'll call it f from A to B. And what it does is it sends you this tuple, D1 up to dr. It just gets mapped to. So what is a monomial? Okay, a monomial, it's just like a type of polynomial. It's basically a polynomial with just one term. So there's just one product that's involved. It's not a sum of products. And what's allowed in the product? They're just non-negative powers of these variables. Monic means that the leading coefficient, or the only coefficient here, is 1. So what you can do is you can just set these to be the powers of the various variables. So this is x1 to the d1 times x2 to the d2, all up to xd to xr to the dr, sorry. So let me just restate that so it's clear. Okay, so this d1 up to dr, this r tuple of natural numbers, now gets mapped to this monic monomial in x1 up to xr, okay, x1 to the d1, x2 to the d2, all the way up to xr to the dr. And let's just check to make sure, of course, if you change any of these. So is this a bijection? Why is it a bijection? So let's just see why it's true. Okay. So firstly, is it 1 to 1? Okay, if you look at the pre-image of any of these, okay, monomials, okay, is there only one element? Okay, so of course there's only one element. You just pull out each of these superscripts, these indices, and that gives you the unique element that it came from. Is this onto? So if you pick any monomial here, does it come from an R tuple of natural numbers? Of course it does, okay? So, and we've said which one it does. You just pull out these indices. So it's clearly a bijection. So in this case, it's very easy to see that they have the same number of elements. And that's why you probably didn't realize that this is actually the proposition which underlies the very important fact that the cardinality of A here is equal to the cardinality of B. And that's a fact that we've used to count the number of solutions here via counting monomials, which is something where you can use generating functions to help you out with. Let's now look at a more interesting example. And here, the first set we're going to consider is AN, and that's going to be the set of n-edged planar rooted trees. So this probably is a concept that is unfamiliar to many of you. So let me just tell you what it is in a simple example. I think it's something that's best not to define formally. When you see an example, you'll know what it is. Okay, so it's a planar rooted tree. So being planar means that we can actually draw it nicely in the planes. So what I have here. So we're going to pretend there's a ground level like this. And then, just as any tree starts somewhere, it's going to sprout branches out. Okay, so we're going to start at this ground level, and it can sprout out from here a finite number of branches. So let's suppose it sprouts out 2 branches like that. And then from these, there's a finite number of them, and it doesn't matter how we put them. The main thing is just how many of them there are. And then from these, they can also further sprout out further branches, or they might not. So suppose this one, maybe it stops here, doesn't sprout out further branches, but this one might sprout out another 1, 2, 3 branches for the next level. And then these 3 branches, they can further sprout out more branches, or they can stop. Okay, so we can repeat this process to build all sorts of planar rooted trees. Now, 2 planar rooted trees are considered the same if essentially they kind of look the same. So it doesn't matter if you sort of move this one slightly over to the left or move this one somewhere in between the other 2. Okay, so motions like that, they're going to be the same. Okay, and that's considered a planar rooted tree. And we're going to look at the set of n-edged ones. So what are n-edged ones? So what are the edges here? There's an edge here, an edge here, an edge here, an edge here, and an edge here. So they're kind of like the branches. Okay, so here's 1, 2, 3, 4, 5. So here n equals 5. So this is a 5-edged planar rooted tree. So it's quite an interesting counting problem to count how many of these there are. Okay, so the way we're going to do that is we're going to compare it by using a bijection with a set that is hopefully more familiar, and this is something that is in the activity sheet on Catalan numbers. Okay, and this is the set, I'll call it Bn here, of Dyck sequences. So they consist of 2n numbers, a1 up to a2n, and these numbers are either 1s or -1s. And there are going to be n1s and n-1s. So half of them are 1s and half of them are -1s. And what is the Dyck sequence? So that is, the Dyck sequence is such that all the partial sums are always non-negative. So if you look at the partial sums of these ai's from I equals 1 up to any spot here, this is always greater than or equal to 0 for m equals 1 up to 2n. So in particular, when m equals 1, right, you just have a1. a1 had better be 1 as opposed to -1. Okay, so it always starts with 1. And as you can see, then of course, you better finish off with a 1, a -1 as well. And so these 2 sets, maybe it's not so clear to you, but actually, they have the same number of elements. And so from the activity sheet on Catalan numbers, we know, the cardinality of Bn is equal to the Catalan number 1 on n plus 1, 2n choose n, and there's a bijection f from an to bn. So if there is a bijection from an to bn, that means that the set of elements in an, okay, the number of them is also equal to the same thing. Okay, there's a 1-1 correspondence between these 2 sets, and then that would imply that they have the same number of elements, and so this is what you get. Okay, so the big question and the thing that I've left unsaid is, well, what is this bijection? So I don't want to establish the bijection for you, but I basically want to tell you, and it's a wonderful exercise for you to figure out why it is indeed a bijection. Okay, so let me tell you how it works. Okay, so how do we go from an n-edged planar rooted tree? So we need to input one of these, and we need to spit out a sequence of 1s and -1s. So remember we're in the plane, so we can draw it like this, and what we do is the following. Okay, so we're just going to go around the tree. So we go around the tree basically like this. We go around like this, and then we go in and come out, and in, come out, and down, and then around like that. As you go up here, you put in a +1. Whenever you go up, when you go up, you go +1. When you come back down, you do a -1, you do a +1, and then here you go back down, you get a -1, and then you do a +1, and then you come back down, you get a -1, and you come back down here, you get a -1, and you do a +1, and then you do a -1. Okay, so let's just go through it again. You do a +1 up here, +1, and -1, +1, -1, +1, -1, -1, +1, -1. So this planar rotated tree is going to get mapped over to what? It'll be 1 + 1 -1, and then +1, and it's -1, then it's +1, and it's -1, -1, +1, -1. Okay, it's this sequence that you have here. If you like, you can put in commas. Okay, so 1 + 1, or +1, -1, like what you see there. Okay, so certainly this gives you a sequence of 1s and -1s, and the first thing that you should ask yourself is, well, why is this a Dyck sequence? Why is the partial sums here, why are they always non-negative? Okay, and the answer is as follows. They're always non-negative because when you see what's going on here and look at the partial sums, right? What's the partial sum after the first one? Okay, it's up here. And that's the first level, so you're up to 1. When you do another +1, you're on the second level here. You're on the second level here, right? So that's a partial sum. Then you go back down, so you go back down to the first level, and you go up. And so basically, what the partial sum tells you is how far you are off the ground, so to speak. And the point is that, well, you can never go below where you started. So you can't go negative in this partial sum. Okay, so that's the key point. So that's the reason why, that gives you a map from a planar rooted tree, okay, over to this Dyck sequence of n1s and n-1s. And Dyck sequence means that it has this condition that the partial sums are always non-negative. So that's the function, and I guess the only thing that remains is for you to show that this is a bijection. And I'll leave this as an interesting exercise for you. But the key point is the following, okay? So remember, what does it mean to be a bijection? That means whenever you solve, so if you're given any Dyck sequence, right, you want to say that there's a unique solution to this map F of some planar rooted tree, NH planar rooted tree, is equal to that Dyck sequence. So in other words, what is that unique solution? And if you know what that unique solution is, that's going to tell you how to do it, okay? So for example, if you're given such a Dyck sequence, okay, you need to know this map is onto, so what's the corresponding planar rooted tree? How do you draw this? Well, you draw it as follows. You try to invert this procedure that you have, okay? So you see the +1, so you're going to draw it going up like this with a +1. Then you see another +1, so you're going to draw another branch coming out like that. When you see a -1, you just come back to the original one, or the previous vertex. Okay, this dot, or what we call a vertex in graph theory. You come back here, and then when you see a +1, you sprout up again. You see a -1, we come back down to that previous vertex. See a +1, we go up. -1, we go down. -1 here means that we go down, back further down to the level 0, okay? And then we do up, so we can add a branch here, and a -1, and that gives you that there. I'll leave it as a good exercise for you to check that this is indeed a bijection, and hence the number of NH planar rooted trees is equal to 1 on n plus 1 times the binomial coefficient 2n choose n. I hope now you can also use bijections to help you count and in your enumerative problems.